Good morning, everybody. Welcome back to Math 105. Plan for today is we are going to continue onwards in Standard 16, where we're going to prove proposition number 11 regarding given a line, how can you draw a line that joins it at a right angle? And then we're going to get into another topic, which is not explicitly one of Euclid's postulates, but is related to Plato specifically, and that's the idea of how do you double a square. And then the idea of doubling a square in conjunction with bisecting angles, which we talked about last time, is going to be kind of our basis for things we can do in Standard 16 that in Standard 17 we'll come back and discover we are not able to do similar sorts of things once we mix it up just a little bit. Got my usual office hours today, 10 o'clock this morning, 2 this afternoon, and tomorrow, 10 in the morning, 1:30 in the afternoon. As far as homework goes, don't forget, Standard 15 quiz is due tonight, and Exam 3 is on Friday, which means no class this Friday. Decided the kind of how the timing for Exam 3 is going to work is that I'll open up the exam probably like Thursday, tomorrow evening, and it'll be due Saturday evening. So you'll have like a 2-day period to work on the exam. And mainly those 2 days will be over the course of Friday and Saturday. So if you want to take it 8 a.m. Friday morning, or for those of you watching from other classes, 9 a.m. or 1 p.m., you're certainly welcome to do so. Any questions or comments before we get started for today? Okay. A medical company figured out how to package basic knowledge in pill form. Student goes to the pharmacy one day and asks what pills are available. Pharmacist says, well, I've got several pills for you. For instance, here's a pill for English literature. Student takes the pill, swallows it, and now has new knowledge about English literature. What else do you have? Asks the student. I also have pills for art history, biology, and world history, says the pharmacist. Student takes all 3 of those, has new knowledge about those subjects. Then the student says, do you have a pill for math? Pharmacist says, oh dear, yeah, wait just a minute. Goes into the storeroom and comes out lugging an enormous pill and drops it on the counter with a thud. That's the pill for math? Student says, looks like it weighs 5 pounds. Pharmacist replies, he always knew that math was a little hard to swallow. Okay, so Proposition 11, which I want to start out with today, is going to be the idea of given some line from A to B, how can we draw another line, say like this, at let's call this point D and this point C. How can we draw a new line that meets AB at a right angle? And just as a quick little bit of review, what does it mean for this line CD to meet AB at a right angle? Anybody remember from Euclid's ideas of what it means for an angle to be a right angle? Exactly, what exactly this means? Because, as a reminder, Euclid does not have the idea that a right angle is an angle with 90 degrees. He had to define right in a way that made 2 certain angles equal to each other.
ACD and BCD would be equal to each other. Neither would be greater than the other.
Bingo. Yeah, we'd like to be able to draw CD so that it connects to AB here, so that these 2 angles, ACD and BCD, end up being equal. So our goal is going to be to find CD intersecting AB so that the angle ACD is equal to the angle BCD. Let me erase here. Any questions about what we're trying to prove? Okay, in that case, we will go ahead and do that. So here's what the proposition says. Proposition 11 says it should be possible to draw a straight line at right angles to a given straight line from a given point on it. So in other words, let's say we're taking the point C here. Given a line from A to B, and given any fixed point on that line, so let's say we're going to choose the point C here, I want to be able to draw a line from C going upwards or downwards that will meet AB here at right angles. So that's going to be our goal. See, how can we construct a line that will do that for us? Here's going to be our proof. We're going to start by saying, let AB be the given straight line. And we're going to let C be the given point on it. And thus, it's required to draw from C a straight line taken at right angles to AB. So kind of what we said, we're going to draw a line that starts at C and that forms right angles when you take the angles of intersection of that line and the original line AB. So the first thing we're going to do is we're going to let D be taken at random. On the line AC. So our first goal is just going to be to pick some point D, and it can be any point on the line segment between A and C. So I'm going to pick my D to be about here. Doesn't matter exactly where. And now that we've taken a point D, we're going to let CE be made in a way that is equal to CD. So in other words, we're going to pick a point on the other side of C, between C and B, about right here it looks like, so that the distance from C to D, a little bit further, about here-ish. I'm picking a new point E on the other side of C, and I'm saying that I'm going to pick E in such a way that the distance from C to D is going to be equal to the distance from C to E. And how do we know we can do this, you might ask? It's going to be that proposition which we've used a couple times in the last few classes. It's going to be proposition number 3 that's going to allow us to do this. To be able to pick a point E between C and B and make CE equal to the length of CD. We're cutting CB short in a way that the point E at which we're cutting CB short will make this line that's left equal to the other line over here. And now, on DE, we're going to let the equilateral triangle FDE be constructed. Which is something our first proposition allows us to do. Is to take this line now going from D all the way to E and to make an equilateral triangle on it. And we're going to call this point F. And then we're going to take the line going from F to C. Our goal now is to show that the triangle DCF is going to be equal to the triangle ECF. In other words, we'd like to show that if we take this equilateral triangle we have and just cut it in half down the middle, the triangle on the left that we get from D to C to F should be equal to the triangle we're going to get from E to C to F. Okay. And just looking at how these two triangles were set up, which triangle postulate do you think, or add one to the postulate proposition jar, which triangle proposition do you think might be most useful here in showing that the triangle DCF and the triangle ECF are equal to each other? Okay.
Side, side, side.
Side, side, side? Okay. So if we look at the left triangle, what's a side on the right triangle that DF is equal to?
Yeah.
Yep, DF's equal to EF. What's one on the right triangle DC is equal to?
CE.
CE, yep. Those are both equal by construction. And how about this right side, CF?
They share it in common.
So just CF is equal to CF? That'll give us 3 equal pairs of sides. And so I think I agree with you. I think side, side, side will be a great tool to say these triangles are equal. So Euclid is going to claim, is going to say that FC has been drawn at right angles to AB. And his argument is basically going to be angle DCF has to be equal to angle ECF because of these two triangles end up being congruent to each other. The fact that they're congruent by side, side, side is going to tell us that all the angles have to be equal. And so in particular, this angle here will have to be equal to that angle there. DCF and ECF will be equal angles. 4. Since DC is equal to CE, that was by construction. We constructed E and so that would happen. DC is equal to CE, and CF is common. And DF is equal to DE. DF is equal to, sorry, not DE, that's a typo in my notes, FE. How did we know, by the way, that DF and FE had the same length? What told us about these two hypotenuses? It's not a word you hear pluralized very often. What about these two hypotenuses tells us that they have to have the same length?
They are also the sides of an equilateral triangle.
Yeah, bingo. It's the fact that DEF's an equilateral triangle here. So since DC is equal to CE, CF is common, and DF is equal to FE, thus, triangle DCF is going to be equal to the triangle ECF, and that's going to be by side, side, side. Because we have two triangles now where all the sides are equal to each other. DC and CE, DF and FE, CF and CF. Hence, angle DCF is going to be equal to the angle ECF. This angle here is going to be equal to the angle ECF, where I've drawn in two right angle symbols. And that's going to be enough because these are adjacent angles to each other. They're angles that are kind of separated by a single line coming down. And that is going to tell us then that those two angles, by definition, are right angles. And they, being the two angles right there, are adjacent angles. And so, angles DCF and angles ECF are right angles. And here, Euclid's going to cite definition 10. Definition 10 is just our definition of what right angles are. They're adjacent angles like this that also happen to be equal to each other. And thus, CF has been drawn at right angles to AB from the given point C. Q, E, we have proved that which we wanted to prove, that given this line AB to start, we could find a line that comes, and at our point C that we wanted to find a line, we were able to find a line that goes down and intersects AB at the point C and does it in a perpendicular way. Hits AB in a way that makes two right angles. Any questions or comments? So I have a question. Here, as part of our proof of showing that we can find a line that intersects AB at right angles, we used Euclid's definition of right angles, which is the one that says we could construct a line that meets ACB such that these two angles are equal. These supplementary angles come out equal to each other. Do you think it would have been easier or harder to find a line that intersects at two right angles if we were using a definition of right angles where right angles are angles with 90 degrees? Think it would have been easier or harder to prove this if we were using the 90-degree definition instead of the equal to its supplementary angle definition?
It would have been much harder because the definition involving 90 degrees is based on measurement, not something we can logically prove.
Yeah, exactly. I would say it wouldn't be as hard as you maybe think, because we could use the fact that all right angles are equal and then say, aha, I have a 90-degree angle here, and this angle is equal to this angle, therefore this angle is 90 degrees. But you're right. I think here, Euclid's choice of how he defined right angles made this proof a lot easier. Just due to the fact that it's logically easier to come up with maybe a way to show two supplementary angles are equal via one of our triangle congruence propositions. Then it's easier to do that than it is to show these two angles have 90 degrees in them. Unless you were to say, well, my protractor says they look like 90 degrees using, a tool that wasn't even around at the time of Euclid. And so here, I think Euclid's choice of definition made this an easier one to work with. Even if it's not necessarily the definition we like or the one we're used to. Ends up being a bit more helpful here. Any other questions or comments about this proposition? So the reason why I prove this proposition is mainly because I want to use this one to help us prove something else. This one isn't one of really the main focuses of Standard 16. Standard 16 is really about, first of all, the proposition from last class where we showed you can bisect an angle. And it's also going to be about this idea of doubling a square. Okay, if I start erasing things? Cool. So this one's interesting, because the idea of doubling a square is not something that's really found in Euclid's Elements. Instead, this is going to come from actually a Socratic dialogue of Plato's. It's going to come from a dialogue of Plato's called Plato's Meno. And what I mean by a Socratic dialogue is it's basically something Plato wrote about a dialogue, a conversation that Plato's teacher Socrates had with someone else in a way that has some sort of great philosophical insight to it. At least in Plato's eyes, and since he'll still call it in our eyes as well. So the way this dialogue goes is something like this to start out. So Meno was a Socratic dialogue of Plato's. Here, Socrates, I'm sure you all know, was Plato's teacher. And Meno was a Greek general. The dialogue was named Meno just after the person that Socrates supposedly had this dialogue with. So this is about Plato's teacher talking to a Greek general at the time. And the idea is Socrates and Meno are having a discussion on whether the idea of virtue is teachable to someone else. Meaning, if I'm a teacher and you are a student, I can teach you many things, but can I teach you to be a virtuous person? They were kind of having a discussion about, is that something that's possible? And if so, what does that mean? And so, during a discussion, on whether or not virtue is teachable, Socrates and Meno are kind of having this conversation. They're trying to decide, is this something we can teach to someone else? Very quickly, they run into a roadblock in that they discover they don't have a good definition for virtue. May have ideas of what it means to have several different things defined at this point, but one thing they do not have defined down to an explicit definition is the idea of what does it mean to be virtuous? Of course, Plato talked a lot about that in his works, but Socrates and Meno, we're assuming, have not put as much thought into this at this point as, say, Plato has. And so they're trying to discuss, what does it mean? And so Socrates is going to propose they seek out a definition for virtue together. So Socrates proposes, all right, well, in order to decide whether or not virtue is a teachable trait, we have to first come up with a definition for virtue that we can agree upon. So Minnow decides, no. I don't think we can find a definition for virtue together, because how can we decide on a definition if we don't know what virtue is already to begin with? Because if we don't already know what the virtue is, how can we try and seek a definition for it? Because if we came up with the correct definition, we wouldn't be able to recognize it. So in other words, if we were to try and come up with a definition, this unknown definition, what would be our metric? What would be our standard for determining whether or not we actually found the correct definition for virtue? In other words, it's impossible to seek what one doesn't know, as one will be unable to determine if one finds it. And in doing so, if we are never able to determine, if we don't have any means to determine if we can find a correct definition for, say, virtue, how can we know anything? According to Minnow, how is it possible to learn any facts, and if we don't already know what those facts are, because we need to know what those facts are in order to come up with a way of being able to recognize that we've discovered it. And so this idea, sometimes called the learner's paradox. The learner's paradox is going to be this idea that it's impossible to discover truth, because you need to already know what it is in order to be able to recognize the truth when you come upon it. Otherwise, it'd be like me trying to tell you, go out into the wilderness and bring me back a flagabar. So you can go out and you can try and look for interesting, exciting things. But unless you already know what a flagabar is, you're never going to be able to bring one back to me. You have to already know what a thing is in order to be able to recognize it. And according to Minnow, that's not only true about, wild beasts in the wilderness, but also of knowledge and facts and definitions. What do you all think about the learner's paradox? I think it's impossible to learn anything unless we already know what it is.
It's impossible to learn anything with absolute certainty, but you can make an educated guess with a really high chance of being correct.
So in other words, all learning is just guesswork in the end?
It's guesswork that gets reinforced with more and more evidence, but it starts out as guesswork.
Okay, so it's educated guesswork then, in other words, you would say.
Also thinking about this from the context of geometry or logic, you might not know how to recognize what you're looking for immediately, but you can gain a greater degree of certainty by building on what you do know, even if you don't know that final thing to begin with.
Okay, so knowledge is sort of like this journey from what you already know, trying to discover more and more by building upon your building blocks. That's certainly a very, I think, a Euclidean way of looking at learning is, all right, we're going to have these things which we just assume we know, and then we're just going to keep building and building and building upon that. Yeah, I think those are both kind of good views on how we could certainly think about this sort of learning. So this is Minnow's idea, was this idea of the learner's paradox. And so Socrates' rejoinder to that, and don't worry, this is going to come back to doubling a square here in just a minute. Socrates' response was he introduced a theory that knowledge is just a recollection of what one already knows before they were born. Of what one's soul already knew before coming into the body. So Menno would say it's impossible to have a definition to come up with a definition for virtue, because if we don't already know what virtue is, how will we know it when we see it? Socrates' response, what if we've already seen it before and we just don't remember it? What if we have immortal souls that have knowledge of many things, or all things, but when they come into a physical human body, they just don't remember? And so the act of learning ultimately then comes down to the idea that we're just trying to remember lost knowledge. Knowledge that was lost when our souls, which were all-knowing, entered our bodies. And this idea, which I never remember how to spell, is the idea of anamnesis. The idea that learning knowledge, is really just, the idea of learning is just recollecting and reintroducing the idea into one's mind that you already knew before you were born. Which is Socrates tried to come up with a sneaky workaround, I would say, for the learner's paradox. Is that maybe you don't remember it. Maybe it's not that that you don't know the definition of virtue. You just don't remember it. But if you were to see it, you would recognize it. I'm not a philosopher. So I'm not going to judge Socrates based on these ideas. Looking around, though, they're all looking a little bit skeptical right now. Which I am too. The idea that, I already knew everything, I'm just remembering it. I don't know about that. But that was Socrates' response. And so Socrates, who wants to come up with some evidence for his idea of anamnesis, decides he's going to put one of Menno's slaves to the tests. Here is where the idea of doubling a square is going to come into play. Proposes he's going to test one of Menno's slaves. Yes, this is a long time ago. Greeks had slaves. And the idea was he was going to test one of Menno's slaves with the question of how, given a square, how can we make a new square whose area is double the area of the original square? And this is going to get into the other thing that we can geometrically do using the tools of the day. Oh my gosh, running out of chalk. Go with these for now. So here's basically what Socrates did, according to Plato. He drew a square like so. whose sides measured 2 feet by 2 feet. And said to Minnow's slave, what would we have to do if we wanted to make a new square whose area is double this one? So this one is going to have an area of 4 feet. How would we make a square somehow using the original square whose area is going to be double that? So how can we use a square with area 4 square feet? Remember your units, Dr. Gerstle. To come up with a square whose area is 8 feet instead. Is that a hand or just a pencil for it?
Thinking, but the idea I had was to build a square off the diagonal.
Make a square like this. That's going to be it, but hold on just a second. So, cutting right to the answer. Nice job. So, first the slave's like, oh, that's easy. You just double the side lengths. You just say, let's just make a square whose side length is 4 feet instead of 2 feet. Just take the square and double the height and double the width. Is that going to work? Why not?
That's going to end up being like 4 times.
Yeah. Unfortunately, if you just double the dimensions, just double the height, double the width, you're going to get something whose area is 16. 4 times 4 is 16 square feet instead of 8 square feet. In other words, the square we would get from doing this is twice as big. So slave proposed, let's just double the height and width. And then Socrates sketched it out in the sand and said, does this look like something with twice the area? No, it's too big. So then the slave's like, all right, fine. Instead of 4 feet, how about 3 feet? We make a square whose 3 feet by 3 feet. If 4 by 4 is too big, why don't we try a 3 by 3? So work that out. And is that going to work for us? Is a 3 by 3 square going to have twice the area of a 2 by 2? Why not?
It's going to be 9 square feet, so it's going to have an extra square foot.
Yeah, it's closer. 3 square feet, 3 by 3 is a lot closer to being double a 2 by 2 than a 4 by 4 was. But it's still too big. So slave proposed 3 by 3. Socrates kind of shot that down. And then the slave's all like, oh, I don't know then. I guess I give up. So then Socrates turns to Minnow and says, it seems as though your slave has given up. Perhaps they thought they had knowledge of how to double the area of a square like this, but now they are known to this fact, and it turns out they didn't know how to do it to begin with. So, at first, the slave thought he knew what he was doing. He knew how to do this, but he didn't. He had ideas for how to solve this problem, but he didn't. But they didn't turn out. They didn't work out the way he wanted them to. And so then, after the slaves kind of out in the dumps and dejected, according to the story, Socrates then proposed a solution to the slave and said, what if we make a square using the diagonals of the original square? So in other words, what if we made a square where this is one of the side lengths? pretend I drew this so that these four triangles were all the same area. That's how they're supposed to look. So, why does this square then have an area that's double the area of the original square?
It has double the number of triangles.
Has double the number of triangles, exactly. Each of these triangles is going to be 1 square foot, because this 2 by 2 square makes up 2 of these triangles, and it has that's not 1, that's 2. 2 square feet. Each of these triangles represents 2 square feet, mainly because there's 2 of these triangles in our 2 by 2 square, which has an area of 4. So you cut 4 in half. Each of these has 2 square feet. And if this triangle, that triangle all have 2 square feet, that's going to mean that the square has to have 8 square feet to it. And so Socrates then showed this argument to the slave of, hey, what happens if we try and use the diagonal of the original square to make a new square? I'll call it this diagonal approach. And what was the slave's response? The slave's response was, oh, that makes sense now. I get it. Yeah, you could use the diagonal and make a new square from the diagonal, and that square is going to have double the area of the original square. And then Socrates turned to Meno and said, oh, what have we here? It would seem that the slave originally thought they were knowledgeable about this. They couldn't remember, though, how to double the area of a square. But then I showed it to them, and now it makes sense. Clearly, they already knew at some point how to do this. They just couldn't remember. And so Socrates claims this was proof, or evidence, I should say, not proof, of Anamnesis. Anamnesis. Every time I try and think of this word, I can't decide in my mind if it's anamnesis or if it's amnesis. Don't worry, you're never going to have to say this word out loud in my class. The idea of anamnesis here coming from the slave knew how to double the area of the square, they just couldn't remember. And then Plato's Meno went on, and they talked about other things related to virtue, and Meno kind of ended up agreeing with Socrates that yes, we can do this because Plato is the person who wrote this, and Plato was a student of Socrates, and so Plato's going to make Socrates look good. But ultimately, this is kind of this famous example in philosophy centered around this idea of anamnesis, where the idea of doubling a square comes from the idea that we can just use the diagonal of the original square to make a new square with that proposed area. Any questions or comments about this approach or this argument to how to come up with a new square whose area is double the area of the original square? The fact that 2 feet was being used here doesn't really matter. We could have replaced 2 feet with like 1 foot or 5 inches or 300 light years long. This idea of splitting it up into triangles is still going to be enough to tell us that, hey, this is made up of 4 of these triangles. This square is made up of 2 of these triangles. Clearly, this new square has double the area of the original square. And the popular retelling of the Meno, though, it's 2 feet is kind of what's given. So what I'd like to do is, Plato didn't include, back to Euclid now. Euclid didn't include this one in the Elements as sort of a logical argument that could be constructed, how to double the area of the square. I propose that I'd like to do is to see if we can come up with a Euclid-style proof of how, given a square, we can double it to find a new square whose area is double the original. And it is ultimately going to come down to this idea of given a square, the original square, we make a new square using the diagonal of the original one. So this is not an actual Euclidean proposition. I thought it'd be fun to kind of try and construct one together. And I'd like to try and use that proposition number 11 that we talked about in the first half of class. The proposition that says you can, given any line, you can find, and any point on the line, you can find the perpendicular to the original line. A line that will intersect at that point and at the original line and do so at right angles. So this is going to be proposition question mark. I'd like to propose we can say it is possible to double a square. Our goal is, let's say this is our original square. And let's say we know the dimensions of this square are 1 unit by 1 unit. 1 foot, 1 inch, 1 mile, doesn't really matter. We're just going to assume that we have a square with 1 unit here. Which means that the area of the square would be 1. Our goal is going to be to construct a new square whose area is 2, whose area is double the area of the original square. And since this is going to take us some ideas, take us a little bit of time, I'm actually going to cut things off here for today. Next class, which will be on Monday, and which will likely be online, we'll continue our discussion of how do you actually double this square as a Euclidean-style proof, with the idea that we're going to be somehow trying to use the diagonal of this square in order to construct a new square whose area is double. Right. Hope you all have a good rest of your day. Quick comment about the exam. I'm gonna go through, make sure everybody's like retests and such are graded by tomorrow, as well as the standard 15 quizzes. So by tomorrow night, you should know exactly where you stand mastery-wise going into the exam. All right, have a good one.